All right, let's dive right in. In the next few minutes, we're going to break down one of the most fundamental forces in our universe, electricity. So forget all that textbook confusion, because together, you're going to master the flow. Ever looked at a circuit diagram and it just seems like a tangled mess? Or is the whole idea of current just not click? If you've ever felt that way, you are definitely in the right place.
And I promise, by the end of this, you're not just going to be memorizing formulas, you're going to understand the why behind them. You'll actually think like an expert.
Okay, so to get this whole electricity thing, we've got to start at the very, very beginning, with the main character of our story, the fundamental spark itself, charge.
So what is charge, really? I want you to think of it like this hidden superpower that tiny little particles have. This power, which we call Q, is what makes them push and pull on each other. It's the source of literally everything we call electricity. And the rules of charge? They're super simple. You've only got two types, positive and negative. And they follow one basic rule. Opposites attract and likes repel. So a plus and a minus will pull together, but two positives, they'll push each other away. And we measure how strong this charge is in a unit called the coulomb, or C for short.
So you might be wondering, what's the absolute smallest bit of charge you can even have? Well, it belongs to a single electron. And this number, look how tiny it is. That just shows you how many billions of electrons are needed to create even a tiny spark. This is our fundamental building block.
All right, so having charge is one thing. But honestly, the real magic, the stuff that powers our entire world, happens when those charges start moving in a coordinated way. That flow has a name, current.
Okay, picture a river for a second. The water itself, that's our charge. But the current, that's how much water is actually flowing past a certain point every single second. It's the same in electricity. Current, which we label I, is all about how much charge is flowing through a wire over a period of time.
And check this out. Here's an awesome trick to remember the formula. In English, you can ask Q IT, which means why did she come? It sounds just like Q equals I times T. It's a really simple, memorable way to lock in how charge, Q, current, I, and time T are all connected. So let's break that down. I is for current, and we measure that in amperes, or amps. Q is our charge in coulombs, and T is time in seconds. But get this, there's a weird but super important historical thing you gotta know. We define the direction of current as the flow of positive charge, but it's actually the negative electrons that are moving. So conventional current always points in the opposite direction of where the electrons are actually going. Crazy, right?
Okay, so we've got charge, and we know it flows to create current. But why? Why does it move at all? Let's be honest. Charges are kind of lazy. They won't move without a reason. They need a push. And in electricity, we call that push potential difference.
You know, the source material had this fantastic way of putting it. Current doesn't flow on its own. It needs a push. Potential difference is the BOP, or father of current. I love that. It perfectly captures that it's the cause, and current is just the effect. No push, no flow. Simple as that.
Now, you probably know potential difference by its more common name, voltage. And the best way to think about voltage is like a slide at a playground. The height of that slide, that's the voltage. It's all that potential energy that's just waiting to be turned into motion as soon as the charge starts to move. It's basically the amount of energy's push that each little bit of charge gets.
And of course, there's a formula for that push. V equals W over Q, where V is our potential difference in volts, W is the work or energy in joules, and Q is our old friend, charge, in coulombs.
Okay, so let's recap. We have a push, that's voltage. It creates a flow, that's current. But in the real world, that flow is never perfectly smooth. Just like trying to run through a crowd, the charges run into obstacles. This opposition, this obstacle to the flow, is called electrical resistance.
And this is the perfect way to picture it. Seriously, imagine you are trying to run down a really crowded hallway. All those people are bumping into you, slowing you down. That crowd is the resistance. In a wire, it's the atoms of the material itself that get in the way of the flowing electrons.
So what actually creates this resistance? Well, it boils down to four main things. First, the length. A longer wire just means a longer hallway with more people to bump into, so more resistance. Second, the area. A thicker wire is like a wider hallway, much easier to get through, so there's less resistance. Then, of course, there's the material itself, and also the temperature.
And all of that gets bundled up into this one neat formula. R equals rho L over A. L's the length, A is the area.
And that funky rho symbol, that's just a number that tells you how naturally resistant a specific material is. And we measure all this resistance in a unit called the ohm.
All right, this is the moment we've been building up to. We've got the push, voltage, we've got the flow, current, and we've got the obstacle, resistance. The one universal rule that ties them all together, that's Ohm's law.
This right here, V equals I times R, is like the celebrity equation of electricity. It's the fundamental relationship in pretty much every simple circuit. It tells you that the push you need is directly related to the flow you get and the obstacle you're pushing against.
Okay, let's see this thing in action. It's actually super simple. Let's say we have a circuit with a 12-volt push from a battery and a 4-ohm obstacle. How much current is going to flow? Well, we just shuffle Ohm's law around a bit. Current equals voltage divided by resistance. Pop in the numbers, 12 volts divided by 4 ohms, and you get a flow of 3 amps. See? It's that straightforward.
Okay, so we get how one resistor works, but circuits almost always have more than one, and things get really interesting depending on how you connect them. The two main ways are in series or in parallel.
And this slide lays out the difference perfectly. Think about a series circuit like a one-lane road. The current has no other path, so it has to go through every single component, and the total resistance just adds up. But in parallel, it's totally different. It's like adding more lanes to a highway. The current can split up, which actually makes it easier for everything to flow, and that reduces the total resistance. If one light bulb burns out in a series circuit, the whole road is broken. But in parallel, the other lanes stay open.
And all of this brings us to one last question, a really practical one. We've talked about the push, the flow, the obstacles, and the two ways to build a path. So, thinking about your own house, all the lights, all the outlets, what kind of circuit, series or parallel, do you think is used to wire it all up? And more importantly, why? The answer is right there in the concepts we've just mastered.